You're about to see planets that break everything we thought we knew about the universe. But number 1 is so impossible, scientists still can't explain how it exists. Number 10, PSOJ 318.5-22. The orphan. Every model of planet formation starts the same way. A planet needs a star. It forms from a spinning disk of gas and dust, gathers mass, carves out an orbit, and stays there for billions of years. PSOJ 318.5-22 has no star. Discovered in 2013 using the Pan-STARRS telescope in Hawaii, this object is roughly 6 times the mass of Jupiter and is drifting through space completely alone, about 80 light-years from Earth. No orbit, no gravitational anchor. It moves through the Beta Pictoris moving group, a cluster of young stars about 23 million years old, but belongs to none of them. At that young age, it is still warm from formation, glowing faintly in the infrared at around 1,100 Kelvin. That faint warmth is the only reason we found it at all. Without a star to reflect, it is invisible in visible light. It either formed like a tiny star through direct gas cloud collapse, or it was violently ejected from a planetary system by gravitational interactions. Astronomers estimate the Milky Way may contain more free-floating planets than stars. Billions of worlds. No sun. Permanent darkness. Number 9. HD 209458b, the evaporating planet. In 1999, HD 209458b became the first exoplanet detected by transit. Since then, the list of what it proved possible has never stopped growing. First exoplanet with a confirmed atmosphere. First with water vapor. First with an evaporating hydrogen atmosphere. It was nicknamed Osiris, after the Egyptian god who lost parts of his body. The name fits. Located 157 light-years away, HD 209458b orbits its star every 3.5 days, 20 times closer than Mercury is to our Sun. The star's ultraviolet radiation tears hydrogen off the upper atmosphere and blasts it into space at over 35,000 kilometers per hour. Hubble observed a plume of hydrogen, oxygen, and carbon escaping in an extended envelope shaped like a rugby ball. The planet moves through space, followed by a comet-like tail of its own escaping atmosphere. The models did not predict this. Hot Jupiters don't just get hot, they get consumed. Number 8. Kepler-16b, the Tatooine planet. The standard model of planetary formation says this clearly. Inside a binary star system, competing gravitational forces disrupt the protoplanetary disk. Planets should not be able to form there. The disk is torn apart before it can accumulate enough material. Kepler-16b is a Saturn-mass planet orbiting not 1, but 2 stars, simultaneously 245 light-years away in Cygnus. Confirmed by NASA's Kepler mission in 2011, immediately nicknamed Tatooine. The 2 stars orbit each other every 41 days. The planet circles both of them in 229 days on a near-perfectly circular orbit. From a hypothetical moon of Kepler-16b, you would watch 2 suns set over the horizon. You would cast 2 shadows. The planet likely formed further out and migrated inward. But its current stable orbit inside the chaotic gravitational field of a binary star system contradicts what the original models predicted. It should not be there. It is there. Number 7. WASP-17b, the backwards planet. Every planet in our solar system orbits in the same direction as the sun's rotation. This is not a coincidence. Planets form from a rotating disk. Everything inherits that direction. It is one of the most reliable rules in planetary science. WASP-17b orbits its star in the exact opposite direction. Discovered in 2009 and located 1,324 light-years away in Scorpius, WASP-17b was the first confirmed planet with a retrograde orbit, a spin-orbit angle of approximately 150 degrees, not slightly off, nearly fully reversed. To produce this, something catastrophic must have happened. Planet-planet scattering likely threw it into a completely different orbital plane, reversing its direction entirely. It is also one of the puffiest known exoplanets, a radius of 1.9 Jupiters at only 0.78 Jupiter masses, density lower than water. In 2023, the James Webb Space Telescope detected quartz nanocrystals in its atmosphere, the first direct detection of silica particles on any exoplanet, sand, floating in the clouds of a backwards planet. Number 6. HAT-P-32b. The giant that should have collapsed. Models for gas giant interiors place strict limits on how large a planet can be for a given mass. If you have too much gas and not enough mass to hold it, the structure becomes unstable. HAT-P-32b has a mass of about 0.86 Jupiters and a radius of nearly 2 Jupiters, a density barely above aerogel. Located 950 light-years away, its orbit sits almost perpendicular to its host star's rotation at approximately 85 degrees. Something violent hit this system and knocked the orbit nearly polar. The current explanation is tidal heating. The same gravitational encounter that reversed the orbit created an eccentric one, and tidal flexing during repeated close approaches converted that energy into internal heat, inflating the planet from the inside. The same mechanism that drives volcanic eruptions on Jupiter's moon Io, but at a planetary scale. Number 5. 51 Pegasi b, the planet that broke the textbooks. Before October 1995, the consensus was firm. Gas giants form far from their stars, beyond the snow line where temperatures are cold enough for ice and gas to accumulate. The inner solar system is for rocky planets. Everyone knew this. On October 6, 1995, Michel Mayor and Didier Queloz announced 51 Pegasi b, a gas giant half the mass of Jupiter, orbiting its star at just 0.05 astronomical units, completing a year in 4.2 days. Dayside temperature over 1,200 degrees Celsius. Some astronomers refused to accept it initially. Surely an error. It was real. Mayor and Queloz received the Nobel Prize in Physics in 2019, partly for this discovery. 51 Pegasi b forced a complete rethinking of planetary science. It proved that planets migrate, that where something forms is not where it stays. An entire field was rebuilt around the implications of one planet that was exactly where it had no business being. Number 4. WASP-107b, the cotton candy giant. The core accretion model requires a rocky core of at least 10 Earth masses before a planet can hold on to the gas needed to become a giant. The core must be massive enough. Without it, the gas drifts away. WASP-107b has a core of approximately 4 Earth masses, less than half the theoretical minimum, yet it is roughly Jupiter-sized, with a density comparable to a marshmallow. Located 200 light-years away, it orbits its star in under 6 days. At that distance, stellar radiation should have stripped the atmosphere away billions of years ago. In 2023, James Webb observed WASP-107b and found an atmosphere thriving with water vapor, sulfur dioxide, and silicate sand clouds. Not just present, thriving, being continuously replenished by a mechanism the models do not yet fully explain. Number 3. Kelt-9b, hotter than most stars. There are hot Jupiters. And then there is Kelt-9b, located 670 light-years away in Cygnus. Kelt-9b orbits a hot, massive A-type star in just 1.48 days. The dayside temperature is approximately 4,300 degrees Celsius. That is hotter than 80% of all known stars, hotter than the surface of a red dwarf. The planet is radiating more heat than most stars in the galaxy. At that temperature, molecules cannot survive. Water, carbon dioxide, methane, all thermally ripped apart. The atmosphere of Kelt-9b is not made of molecules. It is made of atomic ions, calcium, iron, titanium, yttrium, detected by their spectral lines in the vaporized gas. The planet is evaporating at roughly 10 million tons per second. Scientists estimate it has a few hundred million years left before the star evolves and ends it. Number 2. AU Microscopy b, the planet surviving a war zone. Young stars are violent, unstable, prone to massive flares, surrounded by chaotic debris disks still in the process of clearing. Conventional wisdom held that stable planetary orbits couldn't exist this early in a system's life. The environment is too hostile. AU Microscopy IB orbits a star only 22 million years old, located just 32 light-years from Earth. The debris disk around the system is still clearly visible. The planet is literally orbiting through it in each revolution. Hubble and Spitzer detected fast-moving structures in the disk, ripples traveling outward at up to 4 kilometers per second, likely driven by the planet itself. AU Microscopy IB completes its orbit in 8.46 days, receiving intense bursts of ultraviolet and X-ray radiation from its young, flare-active star regularly. The planet is approximately 4.2 Earth radii. By any model, this system should be too chaotic for stable orbits. The planet disagrees. Number 1, WD1145 plus 017, the planet being eaten by a dead star. White dwarfs are the final remnants of dead stars. They no longer generate energy. They cannot form new planets. After a star dies, its planetary system should go cold and silent. WD1145 plus 017, located 570 light-years away in Virgo, is a white dwarf actively tearing a rocky body apart. In 2015, Kepler detected irregular asymmetric dips in the star's brightness, not clean planetary transits, but chaotic, shifting obscurations from a disintegrating object in a 4.5-hour orbit. The fragments are being pulled apart by the white dwarf's tidal gravity as they spiral inward. The white dwarf's own atmosphere contains heavy elements, silicon, iron, magnesium, calcium, that should have sunk out of sight billions of years ago due to the star's extreme surface gravity. They are being continuously delivered. The white dwarf is consuming the debris of its own ancient planetary system, a dead star, eating its own planets, in real time. Subscribe and keep watching.